Alright, so I just want to give you a quick lesson here on 12-4 before you try some problems in class today or for homework. And so this is going to be dealing with angle measures and segment lengths. So our first thing we're talking about here, it says the measure of an angle formed by two lines that intersect inside a circle is half the sum of the measures of the intercepted arcs. If you need to, pause the video, look at this diagram right here, read through this sentence slowly, and then see if this equation makes sense. Alright? And if you do that, that's the first step in learning all these technical math things. They're always hard when you just read through them quickly like that. So always make sure you pause and listen, well, read the math slowly. This is what it means. So far, we've talked about two different types of angles. We've talked about angles coming from the center, so let this point right here be the center, and angles that are on the circle, or we call those inscribed angles. So if we say that this is, say, a 50-degree angle, then we know that the intercepted arc right here must also be 50 degrees because an angle with its vertex at the center is equal to the arc it cuts off. We also know that if it's, if we trace this back, I'll get a different color, this angle right here is inscribed and it's cutting off a 50-degree arc. And notice it's smaller. This angle of rotation here is smaller than 50 degrees. In class I did an example where we had that hoop, and inside the hoop we had that rubber band, or an elastic string, and as I pull this thing further and further back, you notice it gets smaller and smaller until it's about half, what is half, not about, it is half of the arc we cut off there. So this is 25 degrees. What this over here is saying is this. We have a circle again. Let me draw another one of those. But this time, the angle does not have to be at the center, and it doesn't have to be on the circle. We can just pick anywhere on the inside. So suppose we have something like this. Now, when we look at this thing, the question is, what is x here? Well, take note of something. X is not necessarily equal to this arc over here. If x is not, if this vertex right here is not at the center of the circle, this won't be equal to the arc it cuts off. But I do know one thing, is that vertical to this x right here, this angle right here must also be x. Because remember, vertical angles are still congruent. And so these two angles are equal, but the two arcs they cut off are not. And so what this is saying here is, suppose that this arc right here is 20 degrees, and let's say this one right here is 44 degrees. Then x will be basically the average of the two arcs we're looking at here. What do we mean by average? It means add up the arcs, 20 degrees plus 44 degrees, and divide by 2. This gives me 64 over 2, which equals 32 degrees. So both x's are 32 degrees. All right. Now, this theorem, we're just going to roll right through these theorems right here. This is the next one. So we've talked about when we have a circle, we've talked about their angles being at the center, a central angle. We've talked about the vertex being on the circle, an inscribed angle, and we've talked about the one we just did was referring to anywhere inside the circle. It's going to be the average of the arcs it cuts off. Now, go back to where I talked about this being a rubber band, and as we pull it further and further back, the angle gets smaller and smaller and smaller. If I pull it even further outside the circle, this angle is going to get even smaller. And this is what this is saying right here. So notice the vertex of the angle is now on the outside of the circle, and x right here is representing the arc it was cutting off. So here that would have been a central angle. This would have been an inscribed angle, but now we're going outside the circle. So notice each time these angles are getting smaller and smaller. And so our equation is going to reflect that also, an angle that's getting smaller. So notice now, unlike the other two cases where there's only one arc being cut off right here, if it's central, it's just cutting off the x. If it's inscribed, it's just cutting off the x. Now on the outside of the circle, it's cutting off two arcs, this red X right here, and then the blue arc represented by Y right there. And so we're coming up with an equation here, the blue arc X right here minus the red arc Y. So we're taking the bigger arc minus the smaller arc, and then we're going to divide it by 2, or you can say multiply by 1/2. So, for instance, if we have, let's say that we've got a circle here, and here's our angles. This guy's 10 degrees, and this one's 50. And they say, well, what is X right here? It's simply going to be the big arc, 50, minus the small arc, 10, and then divide it by 2. 50 minus 10 is 40, and 40 divided by 2 is 20 degrees. So X is 20 degrees. Now, I want to take a moment here and just sum up a few things. And this is how I'm going to teach you to do it. As we approach the SOL, you're going to have to memorize these equations. And like I've told you before, it's not like these things are really hard or anything like that. It's just when you start to add everything up, you're like, man, I'm learning a lot of stuff here. So, how can I keep all this organized in my head, right? And so let me see if I can adjust these circles so they get a little bit smaller here. I got 4 of them to put in. So when we're talking about angles, and this is pretty much we're after this summary right here, we're done pretty much learning new information about angles and circles. We just got a bunch of different problem types to try out here. We're going to say that we can have several situations. We can have a central angle. We can have an inscribed angle. We can have an angle just any old where it wants to be inside the circle. And we can have an angle outside of the circle. The vertex is outside the circle. And so this is how I want you to memorize this when you want to go through. This isn't on the formula sheet on the SOL. You got to know this stuff. I would call the angle in here X on all of these. Just if you kind of be, systematic with it, it makes it easier. The arc right here, A, whether there's only one arc or 2 arcs. And if there's 2 arcs, call that second arc B. Oops, that was my hand. Sometimes the computer picks up my hand, not the pen. And so all of these are going to be X equals something. So X equals, X equals, X equals. We're just getting the angle by itself. And if it's just the central angle, that one should be really easy. X equals A. Okay. All the others are fractions. And they're all over 2. If there's just one arc, like in this example right here, it's just going to be A over 2. If there are 2 arcs, well, both those arcs can go in the numerator, so I might as well just write A and B, leave a space for an operator there. And do you see how this kind of looks like a plus symbol in here? See, if you kind of turn it sideways, it looks like a plus symbol. It's going to be a plus right there. This one, we know the angle's getting smaller, and typically when we think of subtracting, we're thinking of something getting smaller. That's not always mathematically true. You could subtract a negative, but a lot of times when you subtract something, you're getting smaller, so this one gets the minus sign. So you have only one arc, so it's just A over 2. 2 arcs, you write them down twice. The one on the inside gets the plus, the other one gets the minus. You got to have those memorized on your homework. Practice memorizing them. By the time you get to the quiz, test, and SOL, have them memorized. And we're going to add a whole other set of circles just for segment lengths. So begin memorizing now so you've got that in your head when it comes time. One more note over here. Notice that there's a couple different situations going on with these 3 right here that we didn't really talk about. This one's been like the examples I've been giving you. Notice it's made with a secant here and a secant here. This one's made with, remember what this line is called? It only touches it in one place. That's a tangent. And this is a secant, touching it in 2 places. And then these are what? They're 2 tangents. So either combination that you have on these, so long as it's a combination of a tangent and a secant, two secants, two tangents, whatever, so long as they're meeting on the outside of the circle, that same point, we can have this relationship going on with the arcs where you subtract them and then divide by 2. All right? And then we've already discussed what a secant is, so if you want to pause and read that, you can. I'm going to move on. Let's try some practice problems. So pause the video, try these out, see what you get. This one is our basic run-of-the-mill one where you're just going to add them up and divide by 2. And so when we do that, we're going to get 68 degrees. 46 plus 90 times a half is 68, so x is 68. Now this one's a little bit different because notice on all of our equations, x is the angle right here. So if you go back a couple pages here, we're dealing with it on the outside, and so you got x solved for. So you just got to be aware when you're substituting those things in that, hey, I know that 20 is equal to the big arc, 95, minus the small arc. In this case, the small arc goes from where the tangent line is to right here. Let me undo that and highlight it in a different color so it's a little bit easier to see. So we're going to subtract from that z, and when we subtract from that z and divide by 2, we get 20 degrees. Now it's just algebra 1 stuff. We're just solving for z. Multiply both sides by 2. Subtract 95. And then divide by -1. So 55 is equal to z. That's what we should have down here. There it is. Written in the way the book put it for you there. Whoops. All right. So let's look at a few more of these. You can pause the video, try these out. It's always helpful. Don't just watch me. Pause it and practice it, and then see how I do it, because you'll learn from your mistakes. You can't learn from your mistakes unless you make mistakes. And you're not going to make mistakes watching me. I might make mistakes, but I'm the only one learning them. So on this one, take it you've already paused and tried these out, right? All right, on this one, it's going to be the big arc. Where's the big arc? It starts at that tangent line going all the way around. It's W minus the small arc. The small arc is 110. So W, big arc, minus 110 divided by 2 is equal to 70. Solve for W. Multiply both sides by 2. W minus 110 equals 140. Add 110 to both sides, and 250 equals W degrees. Over here, the big arc, 110 minus 30. The small arc there divided by 2 will equal your Y. 110 minus 30 is 80. 80 over 2 equals 40 degrees, so 40 degrees equals Y. Over here, notice this one. You can't assume that this is the center. In fact, I can tell you it's not the center, because I know that this is 35 degrees right here, which means this must be 35 degrees. And since this does not equal the arc, I know it can't be a central angle. A central angle would be 30 degrees, just like this arc it's cutting off. So I know it's not the center, so it's just anywhere on the inside of the circle. So I'm going to say I know that if I take and average up those two arcs, the x and the 30 here, it means add 30 plus x and divide by 2, I get this angle in the middle, 35. And now solve for x. So 30 plus x equals 70. Subtract 30, and x is equal to 40. Now this is a common problem right here. So pause the video, read the question, and give it a try before I show you the solution. Now, a lot of students will see this and say, there's no way that this can be solved with the information given. There must not be enough information here. But here's how I want you to look at it. Let's first look at this diagram right here. Let me zoom in on that. And let's let this right here equal x. And I think that's what we're wanting to look at, is what is this arc right here that you can see. I didn't even read the problem myself. I've just done this so many times that I just kind of jump in and start working on something without reading it. But I'm pretty sure that arc AB is what we're looking for there, the surface area of the Earth, or the arc measure that the satellite is viewing, if this angle right here is 17.5 degrees. Now, think about how many degrees are in a circle. And let's suppose I told you right off the bat that x was equal to 100. Then what's the arc measure of the major arc BEA right here? Well, you'd say, well, Mr. Burnett, it's 360 minus 100, that's 260. What if I told you x was 200? You'd say, well, Mr. Burnett, that bigger arc then is 360 minus 200. Well, that is 160. What if I told you this x value was 20? You'd say, well, Mr. Burnett, it's 360 minus 20, that's 340 degrees. And so really, whatever I tell you x is, you're going to subtract it from 360. And so let's just make the big arc right here. If this is x, it's not 200, but if this is x, then this big arc is 360 minus x. And so now let's see if we can find out, using that 17.5 degrees, what these other two angles are. I'm going to say the big arc, 360 minus x, minus the small arc, x, all over 2 is equal to 17.5. Do your algebra and solve for x. So I'll do this kind of quickly. This is going to be 35 equals, I don't really need parentheses here. What's negative x minus x? It's negative 2x. So 360 minus 2x equals 35. I canceled out the 2 by multiplying both sides by 2 and got 35. Subtract 360 from both sides. Boom, that cancels. You get negative 2x equals, let's see here, 360. That's going to give me negative 325, I believe. And then divide both sides by negative 2. That should give me x equals, I think it's 162.5. And so there's our value. Now, that's one way you can do this. And this problem comes up quite frequently. You'll probably see it in your homework later on. The other way you can do this problem is this. I know that line A, let's call this point out here Z so we have something to reference. I know AZ is tangent to the circle and BZ is tangent to the circle. So if I draw the center of the circle and draw a line going to A and B, we know from our rules earlier, these must meet at a right angle. I also know that this central angle right here is equal to the arc it cuts off. The arc it cuts off is x, if I'm still letting it be x. And so what I have here, the overall shape, let's get out my highlighter here. See, I got a highlighter somewhere. This overall shape has how many sides? It's got 4 sides. And so I know a 4-sided figure, if you recall from our polygon chapter, 4-sided figure adds up to, or the angles add up to 360, because you use the n minus 2 times 180 rule, right? 4 minus 2 times 180 equals 360. So I've got 90 degrees, I've got 90 degrees, I've got 17.5 degrees, and I've got x. So I know that 90 plus 90 plus 17.5 plus x is equal to 360. Solve for x, you're going to get the same value right here. So there's more than one way to solve that type of problem. And let's move along here. You can read these things if you want, but I want to get on to these next theorems here. Now these next theorems go over segment lengths. So we're going into a different world now. Before, notice these 3 circles here. We've talked about angle measures for these. We've talked about an angle measure here and an angle measure here. But now we're getting into the actual lengths of the segment. So this is talking about length C right here. Nothing about angles. The only thing it's dealing with angles are basically, you notice the vertex changes on these things. So everything you see here are the book's definitions, but I don't really want you writing these down. I'd rather you follow my rules on this. So let me see what I've got, because my rules are going to be a little bit faster to go through these things. And so this is how I typically teach it. Just like we drew out some circles earlier and I said, know these rules, we're going to do the same thing for our segment lengths. So I'm just going to clone a bunch of these out real fast. And if you remember the clown hat theorem, we've kind of already gone over one like it with the clown hat theorem. And so once again, when you go to take your test, quiz, SOL, whatever, you're going to have 4 more circles right here drawn out for your segment rules. So our first segment looks like this. And then we can have 2 secants. And then we can have a tangent and a secant. And then we can have 2 tangents. Memory serves me correctly, that's all the different combinations we could have. And so I'm going to go through and just write on this first segment here, that's going to be an A, going all the way down. Doesn't have to be, but I like to, like I said, be consistent, and you can just systematically just write these things down like I'm doing here. C, 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 and then D. Now, all 3 of these have the same rule, okay? So I'm going to write their rule out here in just a second. This one, this top one, students typically pick up on really fast. And it's simply this. We've got 2 lines intersecting inside the circle. If you take the length of A, which is this little segment right here, and times it by the guy across from him, D, it's the same thing as C times B. So AD equals CB. All right. So that's true every time, and that's what the book is talking about right here. They call it A, B, and CD, but A times B equals C times D. Students never have a problem with that. Now look at how confusing these can look, though. So this is kind of getting into what we're talking about over here, and I can sum it up in one rule. So listen to my rule right here. The rule goes like this. It's the outside part. Make sure you write this down. Times the whole thing. Yes, I said it like that. Thing with an A equals the outside part times the whole thing. Hey, you just said the same thing twice, is what you're saying to me, but that's okay. It's the outside part times the whole thing equals the outside part times the whole thing, and I say that thing with an A for a reason. All right? And so let me show you what I mean by this. I hope you got that down, because I'm going to shrink it down now. The E didn't follow along. He's just going to get deleted. Goodbye, E. Let me just erase a few things here. My hands are making marks as I write on the screen. So this is what we mean by that. Look at this first circle and the 2 secants in it. Look at that first line with C and A on it. What part is the outside part? The outside part is A. So I'm going to write that down. The outside part A times the whole thing. So now the question is, what is the whole thing? Think about that. What do I mean by the whole thing on this line? I don't mean C. A lot of students want to say A times C here. C is not the whole thing. A lot of students want to say A times AC. The whole thing is not AC. If I told you that A was 5 and C was 10, you wouldn't say that, hey, the length of the line is 50. You don't multiply the two. What do? You add them. And that's why I say an A in thing. To remind you, you've got to add those 2 numbers. So it's A, the outside part, times the whole thing, which is A plus C, equals the outside part, in this case it's B, times the whole thing, which is B plus D. There's our equation there. The same thing works for these other 2 circles here. Look at this top line, this tangent. What's the outside part? The outside part is A. What's the whole thing? The whole thing is just A. You don't have to add anything there. It's only one segment. That equals, for the bottom, the outside part B times the whole thing, B plus C. The whole line there. And by the whole thing, I mean start right here where they meet, go all the way through until you hit the circle the second time. Sometimes you'll see diagrams where it stops right here and you got to push that line all the way through and figure out what the whole length is there to use these equations. Lastly, this thing right here goes back to what we called the clown hat theorem. Remember the clown hat theorem where you had the birthday hat on, and as simple as this, if two lines met outside the circle and they were both tangents, and met outside at the same point, to the same circle, then those two segments were equal. This just kind of confirms another way you could look at it. The outside part times the whole thing equals the outside part times the whole thing. Now on all of these right here, we can simplify them and just say, hey, this is a squared, that must equal b squared. Or, as we did with clown hat theorem, that simply equals a equals b, because you square root both sides. This one you can simplify to a squared equals b times b plus c. And so we'll see that most often. But if you follow these rules, you get these three equations, and they'll work every time on those. All right, so it's the whole, the outside part times the whole thing equals the outside part times the whole thing. And we see it over here. Notice on this blue line, this is the book's version now, the outside part, whole thing right there. Outside part, y, whole thing, y plus z. Over here, outside part times the whole thing is t squared. Outside part y times the whole thing, y plus z. So, I don't know what's wrong with these authors, but they need to come up with some catchier spellings there. I feel like all this book stuff, we can skip over a lot of that and get to some real problems in here. So looking at this, try these out. Do the outside part times the whole thing equals the outside part times the whole thing. What's the outside part right here? It's 6. What's the whole thing? Don't say 6 times 8. It's thing with an A. Add them up. 6 plus 8 is 14. That equals the outside part, 7. Whole thing, 7 plus y. Now solve for y. 6 times 14 is 84. 7 times 7 is 49. Plus 7y. I'm just distributing my 7 there. Subtract 49 from both sides. You get 35 equals 7y. Just lost my pen here. Hello, pen. It's not working. 7y. There we go. Divide both sides by 7, you get 5 is equal to y. Is that what they wanted to know? Yeah, I just said find the value of the variable. So 5 is equal to y. Over here, the outside part, z, the whole thing is z. So z times z equals 8 times 24. Remember 24, 16 plus 8 is 24 here. Z times z is z squared. 8 times 24 is what? 160 plus 32 is 192. Just make sure, because I'm doing this in my head, let's make sure we got that right. 192, good. And then the square root of 192 is about, it's about 13.9. I didn't do that part in my head, I saw it right there. So, hopefully those rules help you out there. Let's see, let's do a couple more examples, and then I'm sure you're excited to get on with your homework here. So for these right here, same thing, 14, I'll just set it up for you, you can solve it, but it should be 14 times 34 is equal to 16 times 16 plus x, and then solve for x there. This is one we haven't seen an example of. This is where they meet on the inside, and we're talking about segment lengths. So it's going to be 3 times 7 equals 6.5 times m. So you get 21 equals 6.5 m. 21 over 6.5 equals m. If you want to find the decimal form, you got to do it to the nearest tenth. I don't have my calculator on me, but you can do that on your own, I'm sure. I'm going to flip through these, see if we see any tough ones for you that you can do. Most of these are like the ones I've already done. I'm just trying to find a few in here that are a little more difficult. Now, a couple notes about these. Look at 18 right here. Some students get a little confused about what's going on. They're actually making this problem pretty easy for you because they're telling you what the whole thing is. The whole thing's 6. What's the outside part? X. So it's the outside part times the whole thing, which is 6, equals the outside part 3 times the whole thing, which is 7. So here they're giving you the whole thing. They normally don't do that. So you get 6x is equal to 21, so x equals 21 divided by 6. And you can punch that out. Look at 20 over here. So on this one it can be a little confusing. Notice x is the distance from here to here. And so ignore all this mess on the outside. This is extra fluff here that you don't need. And so notice it becomes one of those problems where you just say 5 times x is equal to y times 9. Oh, wait a minute. Maybe we do need some of that stuff in there. That's one equation I've got set up. Let's see what we can do to figure out the rest of it here. How can I figure this out? Well, I've got a tangent and I've got a secant right here. So let's start with what I know about that. I'll start with the tangent. 11 squared, that's the outside part times the whole thing, 11 times 11, is equal to the outside part on this, which is 7. Well, what's the whole thing? The whole thing is 7 plus x plus 5. Notice that's the whole length of this line. 5 plus x plus 7 is the whole thing, and then 7's the outside part. Well, 7 plus 5 is 12. 7, distribute that 7, you're going to get 84 plus 7x equals 121. Subtract 84 from both sides, and you're going to get 37 equals 7x, where 37 over 7 is equal to x. Still looking for any others I might see that may give you difficulty. I'm sure that everybody has their own opinion on what's difficult, but for this one right here, don't forget looks like you're going to have to use Pythagorean theorem here to figure out this side. And then notice if you move this chord on, remember that rule we learned. If it's coming from the center, meeting it at a right angle, this must also be 5. And so if you use Pythagorean theorem to figure out x here, then you can figure out y by saying xy must equal 5 times 5. Okay? Anyway, those are some hopefully some helpful hints. We're hitting 33 minutes now, so I want to give you a little bit of time to work with a friend in class and finish these problems up. And thanks for watching. Thanks for pausing the video and working hard through each of these examples. And let me know. I'm sure you'll be happy to let me know if you have any problems with these. So thanks for watching, and see you next time.